In this video, we're going to talk about Project 4. And probably the central message I hope you take away from this is that back of the envelope analysis is this incredibly powerful approach to design. And it is really often underutilized by beginning designers. And looking through the results of this project, it seems like there's still some room for incorporating it better into our process. Something you will notice if you talked to really experienced mechanical designers, like faculty in our department who've been designing cool new robots and mechanisms and other things for 20, 30, 40 years. When you talk to them about their designs, they will explain things to you in a way that it's really back of the envelope analysis. They're taking the thing and simplifying it down to its essence and just talking about the very important features and why they work the way they do. They think in free body diagrams, they think in energy analysis, and that makes them good at what they do. And you can get good at this too, because the tools you need are not complicated. These are things that you picked up in statics and stress analysis and physics. It's just the use of them in a sophisticated way at the appropriate times in the design process. So as you go forward, that's something to think about and work on. So I think the best way to demonstrate this here is to go through my process for designing the test robot for this project. I designed a few designs for every project that we do in the class to make sure that the project works and that it's achievable. So here's the robot I designed for Project 4. And where I started, and we're going to do this in 10 steps. The first step is to roughly estimate the payload that we can pull. And to get an order of magnitude estimate of that payload, you don't have to do any design at all. You just start with an energy analysis. So we've got our motor. If we go look at the data sheet, it's rated to put out about 2 watts. If we do that for the maximum allotted time, 3 minutes or 180 seconds, well, work is power times time. So we could do about 360 joules of work. And work is also force times displacement. We know we were going to go 1 meter, so 360 joules, 360 newtons that we could pull 1 meter. And we know that the force that's going to be resisting us is going to be this friction force, mu times the normal force. So 360 divided by some guess at the coefficient of friction, that'll give us about 1 kilonewton. So quickly we can see that we can maybe pull something like 100 kilogram payload, just order of magnitude. Now, this doesn't account for inefficiency in the transmission, and we saw that that could be, a lot of energy can be dissipated there. So maybe, let's say, a really lossy transmission, still we're at about 10 kilograms. And this 2 watts is coming from the maximum efficiency point at 4.5 volts. Maybe we're pushing the voltage, so we might be able to get more power out. Maybe we need to pull 30 kilograms, I don't know. Anyways, you can see that we're in the tens of kilograms, maybe up to 100 kilograms, pretty straightforwardly. And again, this is without doing any design at all. We have a sense of that payload value. Now we'll do a free body diagram of the whole system, robot plus payload. And this is one of the free body diagrams we recommended you do. So our objective here is to have a big mass. And let's just follow through the consequences of this. So we have this big payload mass. Well, it will be subject to gravity. And since the mass is big, that force, that weight force is going to be big too. So this free body diagram is unbalanced. We're going to need something to counteract that force. And it's going to end up being some force from the ground, right? This normal force from the ground. And it will be equal and opposite, right? But if this thing is all moving to the side, then that contact with normal force is going to be sliding. And therefore, there will be a friction force that is pushing the opposite direction of the movement. And that will be coefficient of friction approximately for that payload times the normal force, or mu p times mp times g. Okay, now our free body diagram is unbalanced again. We're going to need some force pulling in the opposite direction. And where's that going to come from? That's going to be from our robot somehow. But what's our robot going to do to produce that force? It's going to be pushing on the ground. And this is a force in shear. So that's going to need to be a friction force. So in order to get that, this pulling force that needs to be less than or equal to the coefficient of friction times a normal force, we're going to need a normal force. Well, where's that normal force going to come from? We're unbalanced again. There's going to need to be some mass of the robot pushing down. And if we notice that this pulling force and this pulling force are the same, and we equate them and do a little algebra, we'll see that the mass of the robot is going to have to be proportional to the mass of the payload. And by the ratio of the coefficients of friction, maybe you can get a little bit better coefficient of friction on your wheel than on your payload. But still, these are going to be of a similar magnitude. And so the thing that we learned from this is our robot is going to need to support a similar weight to that payload value that we just calculated, which could be on the order of 1,000 newtons. So our robot's going to have to be built to take a heavy weight. Step 3, let's do a free body diagram of just the robot. And this is the second free body diagram that we recommended that you do. And we figured out before that we've got this normal force, we've got this friction force, we've got this weight, and then we've got this rope force. This is the thing, you know, we told you need to connect the robot to the payload using a rope. And so that's going to be pulling backwards. So if we look at this free body diagram carefully, we'll see we're not there. There's a problem, right? If we do the moment balance about this contact point of the wheel, you will see that this weight force and the normal force and the shear friction force there, they all cancel. They have no lever arm about that point. But this force from the rope, it does have finite lever arm. So this potato is going to spin counterclockwise. And I draw these free body diagrams like this to emphasize the fact that we haven't said anything about what the design is yet, but we can still make a lot of interesting progress. So we've got this counterclockwise moment. How do we get rid of it? How do we balance this? Well, one way to do that is to add a guide wheel that in this case would be behind the center of mass, and it would create a clockwise moment. And so that's one thing we could do. Another thing we could do that we might have noticed is that we could move the center of mass so that it is not directly above the contact point of the wheel, and then it will have some leverage also. And that would also cause this to create a clockwise moment. Now, if we do some of the moments about this contact point of the wheel, we'll see that, okay, these forces disappear, but we've got the rope force times its height minus the weight times this offset of the center of mass minus this normal force at this guide wheel times the offset there. Now we have these two different ways of counteracting the moment from the rope. Which should we choose? Well, the next thing to remember is that this normal force this friction force that's driving the robot forward, that's equal to the payload friction force, is mu times this normal force, not both normal forces, just this one. And if we do the sum of the forces in the y direction, these two forces have to add up to the weight. And so this normal force will be actually equal to the weight minus the force on this guide wheel. That is, if we say took this weight and put it halfway between our driving wheel and our guide wheel, so that the load is 50-50 in those two, we are paying for the full weight by having this beefy robot that can hold a lot of mass, but we're only getting the benefits, half of the benefits that we were going for by adding that weight, right? Because only half of that normal force is contributing to our friction force that drives us forward. And we're still, whatever normal force we have on that guide wheel is going to result in some friction that actually dissipates some of the energy that's pulling us back. So if we just look at this, we can see this moment caused by the rope is bad, and we'd like to minimize it. So we'd like to make the height of the rope as small as possible. And then the way we'd like to get rid of it is we might need a little guide wheel to stabilize things when you're accelerating. But if we need to counteract that moment, we'd like to do it with moving the center of mass a little bit, not by having a lot of weight on that guide. Okay, now what we can do, now we've got a little bit better understanding of what the loads are and where things should be, we can start to play holes in space. And so here I've drawn, I know I'm going to have a wheel, I've decided early on. So now that I do have some structure to my robot where I didn't have any before. And I know I want a rope to tie into some point. I know that I want that to be low, close to the ground. And I know I want it to be probably kind of close to this hole because I know that these things are going to get connected. So less structure, less mass. I know I have this big weight force pushing down. And I know that I want that to roughly be in line with the normal force. And I'm going to have some little guide force over there. So just from this, and you'll notice this looks a lot like some of those intuitive sketching exercises we did at the beginning of the quarter in projects 1 and more and 2, where we said, okay, I've got this force overfloating in space and I've got this reaction place, and how do I connect them together in an efficient way? Well, we can do that here. We can tie in that skill. And maybe we'll notice that, okay, this thing has to get reacted out maybe here. And, I'd like to get it over to this force, but I can't because that has the wheel has to rotate. So I'm going to come up here and that's going to result in a cantilever. So this maybe needs a taper. And this is just going to be a compression column. So maybe that's going to be uniform. And then there's this little force way far away. Maybe I want to do some sort of like triangle shape. And so we just kind of sketch these things and then glom them together. We can start to get a rough picture of what the overall geometry of our chassis might look like. So now that we are starting to get a little bit more, texture to what a chassis might be, maybe we can start to get a little more detail in our transmission as well. So let's start with the motor and let's choose the set point. So one way to do this would be to say, all right, I know I got to run this thing for a while at high power. I'm worried about overheating. So I'm going to go into my topic reading and get the equation for the maximum current that I can apply without overheating. And that's just going to be something about the maximum temperature, which we know, the environment temperature, which we can also know, the coil resistance we characterize, the thermal resistance, which we've got from our project description, times 1 minus the exponent of the quantity 1 over the time constant. That's going to be RC, the two thermal constants multiplied together, times this finish time, and that will be 180 seconds. So we plug all those things in, we'll get a value for the maximum current that we can sustain for that time without overheating. Maybe we apply some factor safety to it. Then we can say, all right, what do we want our motor to do? Well, maybe we want to operate at maximum power. Why would we think maximum power? Well, we have a fixed amount of time, and in that time, we're trying to do some amount of work that is a force over a distance. The distance is fixed, but we're trying to maximize the force by increasing the payload. So we want to maximize the work done in a certain amount of time. We want to maximize the power. So you could next set the voltage such that the maximum current is approximately equal to 1/2 the stall current. Remember, that's about where the power output of the motor is maximized. And that's very easy to do once you've got the value of the current you want and the coil resistance. And then from there, you can quickly calculate the corresponding motor velocity because you just have the motor voltage balance, right? So this would get you your motor set point. And then you could go to your transmission ratio and say, all right, I've got the motor speed and I've also got the robot speed that I want. I know I want to go a certain distance in a certain amount of time. So the total desired ratio from motor velocity to linear velocity of the robot will just be the motor speed at the set point divided by the robot speed that you want. And then just make sure that that desired value equals the gear ratio of the Tamiya gearbox times the custom gear ratio, if you have one. If you designed some gears in, divided by the radius of the wheel or the effective wheel radius if you've got a little gear, and we'll talk about that more in a moment. Now, one thing that we'll see quickly is that we are limited with how small we can make the wheel radius. It would really help to make this big if, making this big is easy, but this is annoying. But if we can make this wheel radius really small, then it would help us get this number big. But if we try to contact a 2 millimeter radius wheel with the ground, when we have this, more like 2.5 centimeter radius motor, that's not going to work. So that pushes us towards maybe having a custom gear ratio. And it does add some energy loss and some complexity, but it can get us to that operating point of the motor that we'd like. If we don't have the custom gears, things are simpler. But also, we can't operate for as long because if we're at our desired motor speed and we have less ratio, then the motor velocity has to be higher, and also the pull force is going to be lower. Another way you could do it, which is the way I did it several ways, and this is where I ended up, is brute force optimization. You can just try all possible combinations of the things you get to choose and see what works best. So in this case, you could do a nested for loop where you cycle through values of the applied voltage and then cycle through values of the custom gear ratio, if you have one, and the motor current. And remember, you get to choose the applied voltage and the current separately, since your speed may be different for the same applied voltage. And then once you have these things, you can calculate the torque that's coming out of the last stage of your gearbox. And you know that if you're going to connect, say that the last gear is like a little gear that meshes into your gear wheel, say, then really the radius of that last gear is the effective wheel radius. And we'll look at that in a free body diagram. And you can set that you'd like that to be as small as possible, but you'll be limited by the gear strength. And so you could say, oh, let's assume a reasonable value of the face width and then a reasonable number of teeth, solve for the diametral pitch. And that will tell you, the teeth and the diametral pitch will tell you the radius of that last little gear. Then you can account for things like the gear losses at each meshing and in the bearings and the rolling resistance, and finally calculate the pulling force that's possible and the time it will take to pull. And after you do that, check that you haven't exceeded your time limit and you haven't exceeded your thermal limit, which will be time dependent. And this can give you a better answer because, first of all, you're accounting for more of the details in there, so it could be more accurate. And also because sometimes in a task like this that's time limited, it may not be best to operate the motor at its peak power. It might be better to pick a higher voltage and operate closer to the efficiency, the peak efficiency, because we're worried about overheating. And if we cycle through all those combinations and we look at the resulting pull force, so here we're trying a bunch of applied voltages and a bunch of gear ratios, and I'm only picking out the values here that correspond to the best current. What we'll see is that as we increase gear ratio at a fixed applied voltage, you slowly increase the pull force and then drop off where we hit our time limit. And these, these values, we didn't cross the finish line in time. As we increase the applied voltage, you're moving faster. And so you're able to tolerate a larger and larger gear ratio without running out of time. And so the optimal value here for that range that I explored would be this single stage additional custom gearbox. Now, what I actually built was this one because I just wanted to get this done quickly to make sure that it would work. But theoretically, it'd be possible to pull in the neighborhood of that 350 newtons that we back of the envelope at the very beginning. All right, so now we kind of know what we want our transmission to do. We can start to make the components that will accomplish that. And we'll start with this geared wheel. So as we mentioned before, we might want a small wheel radius, but we won't be able to contact the ground. One way to overcome that is to have a wheel that has some geared teeth built into it. And we saw a lot of designs that did this. And some small gear will push on it on a tooth, and that will cause it to want to rotate in this picture clockwise. And then it will have this friction force with the ground that will try to make it go counterclockwise. They'll be in equilibrium. And we see that the radii here are roughly the same. And that means that there won't be effectively any gear ratio here. It'll be as if, in terms of, for purposes of calculating our total gear ratio, it'll be as if that little gear were directly contacting the ground. The forces are about the same. Okay, we've got that. And then we've got our little gear that we're going to connect to the gearbox, and it has an equal and opposite tooth force. And so it's going to need a moment from the gearbox to make it want to spin counterclockwise, and it'll have a reaction force on that shaft as well. And then finally, we've got our gear motor where we have that tooth force is now down. The force from the gear onto the gearbox is this clockwise force, equal and opposite. And then we've got these reaction forces on the feet. And notice that the reaction forces are pointing maybe the opposite of the way that you might think. And that is because this tooth force is going to contribute to some of the moments, say about this point. And the lever arm here is bigger than the lever arm of the little gear, but the force is the same. And so even though the little gear is trying to make this thing, the moment portion here of the little gear is trying to make it spin clockwise, that will be smaller than the moment produced by the tooth force times this lever arm. And so it's actually the net effect of that gear is to make it want to spin counterclockwise. And so we need these foot forces that would, again, make it want to go clockwise. So now we get to map that back into our holes in space. And really, we just have one more choice to make. We've got a little bit better understanding of what's happening at this hole. We've got this, the force of the shaft that's supporting that wheel is going to be up, and mostly up and a little bit forward. And then we need to put this motor somewhere. And so maybe we look at this and say, all right, pretty much I've got the same thing. I've got this cantilever here, and this has a moment that's going to counteract that cantilever. So maybe I can put this somewhere in this region of the root of that cantilever beam. And then my moments that are counteracting each other will be kind of close, and that will make things stronger and smaller. All right, so the last little detail in our sort of sketching of structures here is to think about the next plane over. So we've been looking at this thing from the side for pretty much the whole time. Now, what if we look at it from the top or the front? Here's our little gear, and we've got this tooth force that we saw in the other diagram. And then this thing is connected to this output shaft from the gearbox, and we've put this thing together. We know what this is. And let's work through our free body diagram of this piece. So let's say we're imagining we're going to cantilever this thing. It doesn't seem too bad. The force can't be that big. Let's cantilever it. Okay. Well, we need a vertical force to counteract the tooth force, right? So we can get force balance in the y direction. But right away, we're going to see moment balance is not there. This thing wants to spin counterclockwise. So we're going to need some way of producing a clockwise moment to counteract it. And what's going to happen in real life is that inside the flange that the shaft comes out of the housing of the gearbox through, we're going to have these two forces that are offset by about the width of the flange. And since they're offset, they create that clockwise moment that we need. However, we'll see quickly that this length, if we do say a moment balance about this point, this contact point on the inner edge of the flange, that length to the tooth force is a lot bigger than this length to the outer flange force. And so if we follow that moment balance through, we'll see that this outer flange force, this first one, has to be that length to the tooth contact divided by the length of the flange times the force of the tooth. So we have this ratio of lengths where one is big and one is small. So this is a force multiplier. And just eyeballing it here, it looks like maybe 5-to-1. Now that gearbox is strong, that's true. So maybe we don't need to worry about breaking it, but we do need to worry about the implications for energy loss, because that shaft is going to be rotating, and it's going to have that high normal force, which will lead to friction force. And it has a finite radius, so it's going to have a lever arm, and it's going to be doing work and dissipating energy as heat. And so that's going to be bad for our efficiency. So this is a problem. Another big problem, wherever there's a force multiplier, there's usually an error amplifier, right? And so here I've taken that same diagram and just reduced it to a stick figure, which I usually find easiest for looking at these error geometries. And if we look at this contact point with the inside of the edge of the flange, and here's a contact point with the outside edge, you need a little bit of a gap in order for that shaft to be able to rotate. And so we need some delta here, but that also means that it can rotate in about a different axis that we don't want it to. And this place where the gear is supported is farther away from that inner point. So for the same angle, we're going to get a bigger displacement. And so here we have that the change in the radial position of our gear for a given amount of slop is the length to the tooth divided by the length of the flange. Again, big error amplifier, maybe 5-to-1. And this is especially bad for gears because if they can push out a little bit, click, 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 they can slip past each other. And that will be, we've got some finite pressure angle, so there's always some force that's pushing them away from each other. And so this can be a really big problem. And I think that may have been a limiting factor for some of our designs. If instead we go for this simple support approach, things get a lot better. So here, if we just quickly look at this FBD, we can see, all right, the reaction force at this bearing and flange, where we've got this shaft that's press fit into the other end of our little gear. So it can be supported by a bearing. This bearing force and that flange force are now less than the tooth force. Maybe they could even be about half of the tooth force. So we went from 5 times bigger to maybe half as big, so like a 10 times better situation. And that means that our energy loss there due to that sliding friction will be at least 10 times better. And if we have this little low coefficient of friction from this, maybe it's a ball bearing, then better still. And then our error amplifier has disappeared. And the worst case scenario, the best case would be like, oh, it's like this. Well, then the gear doesn't really move. But if it just shifts a little bit radially, now we don't have any amplification. And the worst case scenario is that we just have the same amount of play as we had in the radial movement of the gear output shaft. Now, something to notice is that up until this point, in terms of the geometry of a robot, we haven't done any actual math. None, right? There's a little bit of symbolic manipulation, but very little. It's mostly qualitative. It's mostly saying, it would be better if this thing were smaller, or this thing were better, or these things were collinear. And that's so many of the important decisions that you make in the design of a mechanism are like that. And that's where so much of the action is. It's important not to get caught up in substituting a lot of numbers or getting, lines and lines of equations early on that can really slow you down and make the back of the envelope analysis less useful. It's best useful when it operates in this kind of space. Okay, so now that we've got, all those big decisions made, catting it up is actually pretty easy and straightforward. Really, we're just kind of trying to turn these 2D sketches into 3D shapes. We're going to add some fillets and chamfers and depth, and think about our print orientation and how thick we want the walls, maybe do a little FEA to make sure we've got the sizes right, ballpark, and do some test prints to make sure our press fits are tight enough, but still something you can get in and take out. And we're there. And in my case, I don't know, this was just maybe 3 hours of work total to get this part done after all the other stuff was was set. That was where the thinking came in for the design. And so for this particular, now this is not like the be all end all design or anything, but here's an example of a design. And this is the test one that I built for this project. And you can see we've just got one meshing point so that we can get a smaller effective wheel radius. And here's a slow motion version. And that's meshing with this gear wheel, little rubber band to get the slightly higher coefficient friction with the ground. You see there's that low rope contact point so that we don't get too much of a pitch moment. Sort of a tapered cantilever there, straight up column to get the weight here. You can see these are weights, a bunch of steel resting on top of it. It's carefully maneuvered so it's almost exactly over the axle there. Got a couple little dainty balancing wheels that don't get engaged too much. That gear on the output of the gearbox is supported by a bearing here so that it's in simple support. And you can see that the main wheel there is also simply supported. And there you have it. And I never did get this up to the maximum weight. I ran out of weights. So I looked for a heavy object that I had around the house, and I was able to get one of my children to sit on this, but I needed both to stand on that book to see if we could get closer to the 1,000 newtons, but I could not quite get that to happen. But they seem to enjoy the ride. So this is all intended to show you that you can do this. You have the tools to do this. You absolutely can. It's about back of the envelope analysis. It's these simple tools we've been picking up our entire career as engineers, from ME1 through E14, introduction to mechanical engineering, statics, stress analysis, physics, and really it's the sophisticated application of these things and using it at the appropriate time in the design process that's differentiating. So if you take one thing away from this project and this class, it is try to use that back of the envelope analysis. Use it early on, use it frequently, and use it to make design decisions. Usually there's a way to see a good path without actually designing any real hardware. You can get very far in these designs without committing to a particular layout or anything like that.